And now we are going to talk about the accuracy. So recall that we can use the accuracy, the fraction of correctly classified labels to measure the performance. However, accuracy is not always a useful metric. So consider a model for predicting whether the bank transaction is fraudulent, where one where only 1% of transactions are actually fraudulent. We could build a model that classifies every transaction as legitimate. This model would have an accuracy of 99%. However, it does a terrible job of actually predicting fraud. So it it fails to it fails at this original purpose. The solution where one class is more frequent is called class imbalance. So one class is more frequent, that is one class imbalance. Here, the class of legitimate transactions contains way more instances than the class of fraudulent transaction. This is common situation for practice and requires a different approach to assessing the model's performance. So, confusion matrix for assessing classification performance. Given a binary classifier such as fraudulent transactions, example, we can create a 2x2 matrix that summarize performance called confusion matrix. Assessing a classification performance across the top or the predicted labels. Across the classification performance and down the side are the actual labels. Okay. So the true positive are the number of fraudulent transactions correctly labeled. And the true negative are the number of legitimate transactions correctly labeled. The false negative are the number of legitimate transactions incorrectly labeled. The false positive are the number of transactions incorrectly labeled as fraudulent. Okay, as usually, the classes of interest is called the positive class, as we aim to detect fraud. The positive class is legitimate transaction. So why is the confusion matrix important? Firstly, we can retrieve accuracy. It's the sum of true predictions divided by the total of the matrix. Precision. Secondly, there are two other important metrics we can calculate from the confusion matrix. Precision is the number of true positive divided by the sum of all positive predictions. It is also called the positive predictive value. In our case, this is the number of correctly labeled fraudulent transactions divided by the total number of transactions classified as fraudulent. High precision means having a lower false positive rate. From our classifier, this translates the fewer legitimate transaction being classified as fraudulent. Recall. Recall is the number of true positives divided by the sum of true positives and false positives. This is also called sensitivity. High recall reflects a lower false negative rate. For our classifier, it means predicting most fraudulent transactions transaction correctly. So the F1 score is the harmonic mean of precision and recall. This metric gives equal weight to the precision and recall. Therefore, it factors in both the number of errors made by the model and the type of errors. The F1 square favors models with similar precision and recall. And this is a useful metric if we are seeking a model which performs reasonably well across the both metrics. Now, in confusion matrix in Scikit-Learn, using our chart data to compute the confusion matrix, along with the matrix, we import the classification underscore report and confusion underscore matrix from the Scikit-Learn dot matrix. We instantiate our classifier, split the data, fit the training data, and predict the labels of the data set. And confusion matrix in Scikit-Learn, we pass the test set labels and predicted labels to the confusion matrix function. We can use, so now can see 1106 true negatives in the top left. Classification report in Scikit-Learn. Pass the same arguments to classification report, outputs all the relevant metrics. It includes precision and recall. By passing 0.76 and 0.16, the Chorn class respectively, which highlights how poorly the model's recall is one on the Chorn class. Support represent the number of instances for each class with the true labels. Yeah, let's practice. So the same data set I'm taking here, Chorn data set. This is the Chorn data set. There is this is the data set, and see the confusion matrix. So 1126 and 30. These are the true positive, and 38 is the true negatives, and 0.76 and 0.19. The appreciation is 0.76 and 0.19. So the model performance is performing badly. So diabetes data, I'm taking another data set. Again, I split the data. These many data sets are there. So here 1105 are the true positives and 40 are the true negatives. So here this is how the model performance, 0.47 precision, 0.5 is the recall, and 80. So this is the precision. These are the precision. This is okay. Thank you.